We're coming now to the next session, artificial intelligence. We have the same way 4 presentations, and you know we are short in time. And the first presentation will be from Sören Discher. He is in a company, Point Cloud Technology in Potsdam. And yeah, he is specialist in such things, and I'll give it to you now. Please.
Right. Test. Yes. All right. Yeah. Thank you very much for the introduction, and good afternoon, everyone. Let's take a moment. There we go. All right. In the next few minutes, we will take a look at how the monitoring of foods can be improved to an extent by applying AI, in particular deep learning, to regularly captured 3D scans of food trees, in that case. And such scans of trees and other objects are usually also commonly known as 3D point clouds. That is, 3-dimensional digital representations of real-world objects that can be captured automatically and that we at Point Cloud Technology are working with on a daily basis. Maybe some background. We are a software company, so we don't capture any data ourselves, but instead we provide IT solutions for the management, the computational use, and the visualization of point clouds provided to us by our clients from academia and industry. And one of these clients is the ATB, with whom we are working together with partners across Europe and Israel on the CrackSense project. The project itself has already been introduced earlier today by Avi Sadka, so I'm going to go rather briefly over the slide. The general idea here is that we want to automatically scan orchards in regular intervals, and then we want to analyze the resulting temperature annotated point clouds to identify individual foods, and then further, alongside with a number of properties for each food, like the surface smoothness, the surface temperature, the wetness level, and all these properties can then be used to, at least we hope it can be used, to assess the risk of food cracking, which hopefully in the end helps reduce yield losses. All right, I think not everyone in the audience is familiar, especially with point clouds. So maybe just a brief summary. Point clouds are a special kind of 3D data that can be created automatically by means of in situ or remote sensing technology. For example, we may use laser or LiDAR sensors that automatically scan the environment, or we may use an image-based approach where we apply software to transfer a set of 2D images of an object into a digital 3D representation of that object. And these sensors can then be attached to any kind of vehicle, like drones, airplanes, cars, trains, submarines, or they may be used in a more stationary setup. They may be mounted onto backpacks, for example, or they often come as handheld devices nowadays. Like every modern smartphone usually also comes with an ability to capture point clouds out of the box nowadays. Right, so how does such a point cloud look like? Well, something like this. Here we are looking at a road environment point cloud, so a slightly different use case, slightly different object scale, but we can still identify some of the unique properties that hold true for all point clouds regardless of the use case. First of all, point clouds are generic in the sense that surfaces are approximated by irregular point samples, and they are also quite simplistic because they neither model nor reflect any topological surface properties directly. So when we look at this point cloud, we may be able to visually identify certain objects like cars, traffic lights, and so on. But such object information are never stored directly within the point cloud. Instead, we have to derive such information in a separate processing step by analyzing each point's local environment, by calculating and combining certain properties. For example, the average surface normal across all points within that highlight area, or the surface curvature. And all these properties can then be used to calculate the most likely surface category of each point. In that example right here, for example, every yellow point represents most likely some part of a car, every red point represents some part of a building, and all the green points represent vegetation, and so on and so on. All right. And once we have such a semantic segmentation, we can go a step forward and cluster neighboring points with similar characteristics or similar classes into objects, so that we end up with a list of distinct objects within the point cloud that we then may further analyze depending on the use case. And while in this example, of course, we operate on a much larger object scale, the same approach can also be used, for example, to identify individual fruits within a tree, as long as the captured point density is sufficient, which is definitely possible with nowadays technologies. So let's have a brief look into how the semantic segmentation of a point cloud works behind the scenes. Again, we are looking at a different data set from a different use case, but that doesn't affect the general approach. Now, traditionally, point clouds are classified via a metrics-based or rule-based approach. That means we compute or extract predefined metrics for individual points or point groups. That could be different color values, RGB color, infrared color, surface normals for each point, the localized surface curvature, and all these different matrices can then be used in a rule-based system to identify the most likely semantic class per point. And that works decent enough for when you have few classes with clearly distinct surface characteristics. In this example, for example, we only have to differentiate between flat building roofs, ground, and fuzzy vegetation. But that such a rule-based system can easily get extremely complicated the more classes we add to the equation, and whenever changes to the characteristics of captured data occur. For example, if we now want to capture point clouds with a much different density, we might also have to change our internal rule-based system. So because of that, it's increasingly complicated to use such a manual rule-based system, and instead it's become more and more popular to instead use a deep learning-based approach. Behind this are artificial neural networks, the concept of which is depicted in a highly simplified manner in this illustration. So the idea is that we still have rules, but instead of manually defining such a rule set, we let a neural network learn the characteristics of individual categories in an evolutionary way. In that example, the network could learn, okay, what are typical properties and traits of a dog compared to a wolf? But that could just as easily be applied to, okay, what are typical features of an apple compared to a cherry, and so on. And the network does this based on already classified data sets, which we need to have, of course, first, and then it returns a probability for each endpoint. So fundamentally, the approach is always the same. Before we can feed new data into the network and predict our classes, we first need to train that respective neural network. And that is done using suitable training data. Generating such data can be requires manual effort, but as we can see in this video, using proper tooling, we can easily facilitate that process. Right, that was a lot of theory from other use cases. How does this apply to our use case of monitoring foods? Well, in that project, we also use point clouds. Right, we have a 2D LiDAR sensor in the field that detects the raw point cloud data. That sensor is combined with a thermal camera and an RGB camera that provides optional RGB data that could also be mapped onto the point cloud. And all these sensors are then attached to a rack that can be used directly in the field to capture the data. For more information about that specific data generation or capturing process, I refer to our project partners, in particular the ATB. Important or relevant in this talk is that in the end, we end up with a point cloud of each step of each tree, and then we want to further process and analyze that specific point cloud. So to identify individual foods or food clusters within such a point cloud, we plan to apply a deep learning-based semantic segmentation, similar to the one we just saw, followed up by a semantic clustering of neighboring points. And then in a second phase, we also plan to apply statistical clustering to further, based on different metrics such as surface smoothness and surface temperature, to define a wetness level for each food, ranging from completely dry surface to overall wet food surface. And that can then be used by our partners to further predict food cracking. As a very first step, though, as I mentioned, we first need to properly train the neural network, so we need proper training data for that, and we are right now in the process of training the neural network because we just received the very first data sets. So what we are seeing on the next slides are first preliminary results of the semantic segmentation that we expect to improve constantly over the next months. Here, for example, we can see preliminary results for pomegranates. We can see the point cloud on the left visualized or colorized by each point's intensity value. And the point cloud also contains point-specific surface normal and local surface curvature values. Both these attributes are computed in an additional processing step by analyzing each point's local neighborhood. And when we now colorize based on the semantic segmentation, we can see that the majority of visible pomegranates within a tree were identified correctly. Right, and when we now map the temperature data onto the point cloud, we can also see that, at least in this example, we can clearly see that there's a visible temperature difference wherever foods are located. All right, and obviously and aside from pomegranates, we're also training on apples. As you can see here, again, we can visualize the point-specific intensity, surface normals, or the local surface curvature. In the case of apples, the initial results are not that good right now. They're improving, and we're making good progress. And the same can then be said for cherries pretty much. So we again have intensity values, follow up with surface normals and local surface curvature. And we also have already initial results for cherries that we expect to further improve over the next month. And we also plan to give a final update on that at the Food Logistica next year. At this point, however, for now, we can conclude that state-of-the-art remote and in-situ sensing allows to quickly generate digital 3D models of orchards at regular intervals. And we believe that deep learning approaches for 3D point clouds have the potential to also identify individual food or food clusters automatically. And we further believe that we can then use established cluster analysis algorithms on classified point clouds to determine wetness levels and assess cracking risks automatically. However, all this depends on having sufficient sampled data and adequately trained neural networks behind it, which for the specific use case is what we are doing right now. So we're looking forward to present the full results next year. And for now, I'm happy to present, to answer any questions you may already have. Thank you.
Thank you very much, Sören. And we have only time for one question. Maybe one question. What do you think, how long it will need until these systems are possible to bring into the practice?
Yeah, so I think just the system from our side where we process a point cloud and get the results, I think that should be ready within this year. So this is when we plan to finish it. And I think from that point on, the rest is probably mostly a mechanical problem. So yeah.
Okay, thank you very much. Again, and then. Okay, the next presentation will come from Dr. Cesar. Good look. He is in the data science group at ATB, and he will talk about explainable artificial intelligence. How can we trust deep learning? It's, I think, a very interesting topic. Yes.
Thank you very much. My name is Cesar Kutluk. I'm also with ATB, and I would like to give a brief introduction to explain AI and why it matters. I believe many of you, and actually many of the people around the world are using AI now, but this wide usage also comes with risks and an increasing need for trustworthiness. So if I ask you why do you think these are apples and oranges, most probably you will tell me that the size, shape, or other visual cues or features that you associate with these types of fruits are the basis for your decision. So you can tell me your reasoning mechanism that led to your decision. These kind of images are very easy for the current state of the art in AI. So they can also classify these kind of images. They can recognize apples, oranges, or much more complex problems. However, they are black boxes, so we don't know their reasoning mechanism, how they reach to a decision. And especially in high-stakes applications, including food security or food industry or agriculture, healthcare, etc., these can have catastrophic reasons. So explainable AI is one step towards achieving transparency and trustworthiness in AI. Before moving into the details of explainable AI, I would like to give a brief information about how AI is built, AI models are built, and how they are deployed in production environments. So in the standard way of AI building, we collect data, we pre-process them, we do some feature engineering if our algorithms or models require it. We select an architecture, we train our model on the training set, we do some hyperparameter tuning and validation testing, etc. And in the next stage, this is more like the practical side of things, more onto the software engineering kind of work. It includes model optimizations, scalability, or how we achieve load balancing, etc. And also monitoring how the model will be, or how the users will be communicating with the AI model. However, we are not focusing much on the trustworthiness topics such as explainability or transparency, uncertainty, robustness and security, bias and fairness, and ethics and compliance. So if we want our models to be used in large-scale applications, and if we want to avoid these catastrophic results, depending on the nature of our problem, we need to focus on these extra layers of work for trustworthiness too. And today I'm talking about explainable AI. We have seen some information about how we train AI models. So we collect data, we train our AI model, and we can use it for making predictions. However, as I said before, these AI models, especially in the deep learning era, are black boxes. So we don't know what's going on inside it. We know the mathematical functions, but the large number of parameters are tuned by using solely the data. So we don't exactly know what's going on, what's the reasoning mechanism. And we measure the performance in the standard way of things. We measure the performance based on accuracy and relevant metrics. So if the decision of our model is apple in this case, it's a correct decision. If it's an orange, it's a wrong decision. On a test set, we calculate the overall performance of our model. And if the overall accuracy is, for instance, 93%, maybe we can think that it is good to go. So we can pass it to the deployment team. They can integrate it to the product. But do we really think that it's good enough? I'm saying this because the model can make the correct decisions and incorrect decisions based on right or wrong reasons. So explainable AI can give some transparency, so we can be more sure that that kind of accuracy metrics can be trustable. I would like to give some examples. So these images are from the Pascal Visual Object Classes dataset. Let's think that we are, again, training an image classifier, maybe based on convolutional neural networks or transformer-based architectures. So we collect some images. In this case, we see horses and dogs. And we train our AI model, and we have the black box. And we want to make a prediction for this image. But our AI model says it's a horse. We need to understand why, because we have the black box model. We don't know what caused this misclassification. So this is where explainable AI algorithms come into play. By using a local explanation algorithm, we can get this kind of visuals. So in this example, we see that it focused on the bottom left corner, and there's a text. If you want to do further analysis, we can go to our training set, and in the Pascal VOC dataset, we see that a very similar text is located at the same location in the horse images, in the training set, I mean. So we can conclude that the model has focused on some false regions or false associations, which are also known as spurious correlations in the statistics literature. And this phenomenon is also known as shortcut learning, mostly in the medical AI literature. Actually, in AI, this is also known as the Clever Hans problem. Clever Hans was a horse, which was, people thought that it could do arithmetic operations. But it turned out to be that it associated some subtle cues, gestures of its owner to some outputs. So actually, he's not a arithmetics. He doesn't have the arithmetics capabilities, but he just can make the correct decisions based on these false associations. For this presentation, I wanted to simulate this shortcut learning on another data set. Again, it's a very simple image recognition example. I selected some subsets of apples and oranges from the Fruits 360 dataset, and I added a watermark on the apple images. And after training the algorithm, I tested it on orange images, and for some orange images, I added the same text on the same location as well. Here we see two different explanations by using two different post-hoc explanation algorithms, and we see that when we add the label or the watermark text, we see that the model starts to focus on that area. And I said that these algorithms are called post-hoc algorithms because we run them after the model makes its prediction or reaches to a decision. And they are also called local explanation algorithms because they generate explanations for a specific single input. Of course, the examples I have shown are very simple examples, RGB images, and a single object is there. But for instance, at ATB, in the other presentations, we have seen that we work on very complex data sets, heterogeneous data sets, from microbiome data to hyperspectral images to point clouds. So we try to put some effort into bringing transparency to all of our methods or all of our projects. Here we see one example for backscattering image of plum fruits. This can be used for the sorting line, and by using explanation methods, we can bring some trustworthiness. As I said, those algorithms are local explanation methods, but there are many of them, and there is also the other category of global explanation methods, which try to explain the general behavior of AI models. And there are many well-maintained explainable AI software. For instance, for these visuals, I used Captum and TorchCam libraries. So I recommend checking them if you are working on AI and if you want to bring some transparency to your models. So we should not rely solely on model accuracy. We need another layer of trust, and explainable AI is one step towards that. So transparency is essential, especially in high-stakes applications like food security, food production or healthcare. And these kind of works are also necessary for regulatory compliance and certifications. There are also other trustworthiness topics which can also be important based on the nature of the project. Thank you very much.
Thank you very much, Cesar, for your presentation. We have time for questions, please.
Thank you for your presentation. I want to ask, can we train ethics to the AI models? Is it an impossibility to do it?
So AI ethics is a whole research area. Some people are working on that. I don't know much about it because I haven't worked on it, but for instance, maybe you've seen some incidents for human recognition software based on AI. They did some very bad things. I don't want to tell them.
I'm just like the because like the if we can, I think like the train them like the good ethics, like the we can trust them in some way and without these errors, like let's say.
So there are many things that can be done. For instance, you can make your data set more diverse, and you can check the data set in terms of ethical concerns or bias, racial bias, I don't know, gender bias kind of concerns. And these will all contribute to the AI ethics.
Thank you.
Okay, thank you very much. And we'll come to the next presentation from Helene Foduovo Marcuate. Sorry, I have problems with the pronunciation. She is from the University Pretoria in South Africa and still in the moment at ATB. Helene, please, it's yours.
Introduction. Oh, can you hear me? Yeah, okay. Good afternoon, everyone. So today I'll be sharing with you a preliminary study on how AI-generated post-harvest data can be used to further improve food storage. Excess solar radiation, elevated temperature are the main cause of abiotic stress on food skin in orchards. Those conditions can also cause suppression or andocyanin accumulation that can result in low pigmentation on fruit surface. Other physiological disorders caused by those conditions include sunburn, impairment of photosynthesis, and negative impact on food quality and storability. The severity of those disorders also depends on the position of the fruit in the canopy. Coating is one of the techniques that have been used to prevent sunburn and increase shelf life. Next. Okay. So the objective of this study was preliminary to evaluate the effect of canopy position on fruit quality, and secondary to investigate the physiology and storage stability of apple treated with bio-coating during pre-harvest. So the study was conducted in a commercial orchard near Potsdam. 45 trees were used, and microclimate of the canopy was collected. Microclimate data of the canopy was collected. So the study consisted of 3 treatments. The first treatment, pre-harvest treatment, for this treatment, you have to differentiate between exposed and shaded fruit. Okay, so we did that based on the temperature, and we used the terrestrial mobile sensor system, commonly known as TOMI, to do that. I think our previous speaker spoke extensively about point cloud and so on, so I will not say much about that. So basically, these are the point cloud. Example of point cloud that have been extracted from the TOMI. So it's based on this temperature that we're able to differentiate which fruit is exposed and which fruit is shaded. The second treatment was a bio-coating treatment. So basically, we apply bio-coating on the fruit. We apply both on shaded and exposed fruit. Okay. After harvest, the fruit were then stored in cold storage. There, the fruit were again subdivided. A group was stored in cold storage, and the second group also was stored in cold storage and controlled atmosphere. So the measurement, we took 3 measurements at harvest and also at 2 storage periods. Fast forward to the result. This is the firmness. Okay. There are evidence that fruit that are exposed to excess solar radiation have high firmness. Okay? But in this study, we can see that with fruit that were stored in the cold, but we cannot assign that to sunburn because that was not obvious with other treatments. Okay. What's obvious from this study is that the controlled atmosphere storage and the coating help maintain firmness throughout the storage. Okay, I should have shown that. Okay. Here is a total solid soluté. Basically, this is one of the parameters that I use to measure the quantity of sugar in the fruit. Okay. Here also, there's the amount of total soluté in exposed fruit was expected to be higher compared to shaded fruit. But that wasn't the case in this study because the results were very inconsistent. Okay. But what can be noticed here is that fruit that were shaded had lower total solid soluté, lower content in sugar, even after storage. That is probably due to the delay in ripening. In other words, delay on the biosynthesis of carbon products. The U angle basically is a measurement of one of the measurements for the color of the fruit. For this study, the U value was high in internal fruit. Okay, I think in my introduction I mentioned already that fruit exposed to high temperature or excess radiation, in food exposed to high temperature and excess sunlight, the accumulation of anthocyanins is impaired. So that's evidence in this study because if you can see here, all the internal fruit have higher anthocyanin content compared to fruit that were exposed to the sun. Okay. So briefly, as take-home message, solar radiation, high temperature compromise fruit quality, such as firmness and color, as shown in this study. The previous application of coating may protect fruit from sun damage and extend shelf life. Advanced automated sensor allow monitoring of fruit temperature, timing, and more target action in crop management. That is it for me. Thank you so much. Thank you for your attention.
Thank you very much for your presentation.
Pleasure.
I think we have enough time for several questions. Please. Okay, then I have one question to you. Coating in pre-harvest.
Yes.
How do you treat the fruit? Do you spray the whole tree, or how does it work?
Yes, in this case, because we have decided on which ones should be considered as external and which ones considered internal.
The micro.
Oh, sorry. I'll keep moving the microphone, right? So yes, we spray the fruit, all the fruit. After you have decided on which one should be considered external and which one is internal.
Okay.
Yes.
Because it should be not easy.
Not at all.
Are there other questions, please?
No, this is a product that have been conceived. Which one exactly, please?
Spraying.
The spraying, not yet. No, there's something that was done in the lab. Yes.
Other questions? Okay, again, thank you very much.
Pleasure, thank you.
Okay. Now we'll come to the last presentation from Manuela Zudesase. She is senior scientist at ATB, and she is a scientist in precision fruiticulture, and she will give us a presentation about AI supports from crop management in apple and grape production. And important is, Manuela is the organizer of these whole sessions, and therefore I will say thank you very much.
Yes, thank you so much, Martin. Thank you so much to the Fruit Logistica to give us the opportunity to be here. And actually, thank you to all of you. probably you're always one step already in the plane or in the train or something. So I'm happy that you stay here a little bit longer. Yeah, we would like to support crop management a little bit more with something which is affordable for the farmer. And we thought a mobile app would probably do the job here. So we wanted to approach a mobile app in a situation where we have global warming. We see a lot of heat stress into the orchard. Randomly, we just heard it in the presentation before and also in the morning already. So what we defined as our tasks was, well, we would like to have a mobile app as a tool to help farmers to know when the risk appears that the fruit get damaged from excessive heat. So if we have a heat wave, we should somehow characterize how the spatial temperature distribution is into the orchard, because it could be that the whole orchard is affected. It could also be that only a part of it is affected, or even only part of the canopy is affected. So we were thinking, what kind of technology could we use for that? And obviously we can glue some thermocouples on the fruit directly, so that we will know the temperature at the fruit level. But that is kind of tedious. Also, we wanted to measure on many fruit and not only on the few where we could place the thermocouples. So we thought that maybe, first I have to define what is a fruit damage, right? So, but then I come to this technology where we see the temperature. So first talking about the fruit, so the damage, how it would look like. So in apple, just as a rough estimation, are above 45 degrees Celsius. We see something like these bleaching that we see here on the left. That is normally reversible, but as soon as it gets this browning effect, that what we see more severe in the middle, in the center image, then this is really something that is difficult to market. And we may see an influence on the storability, what we also heard in the presentation before. So, and then if there is necrotic damage, so then it's too late. So that appears above 50 degrees Celsius approximately. Obviously, it depends on the variety, but just as a threshold that we can go for. So that is in apple. In grape, we also see similar things. So for example, we can see the shriveling of the berries. We can see discoloration, so the upper ones are normal white-green berries, the lower ones also got some browning effect, so oxidized polyphenols basically. So that are the damages. So, but we didn't really want to go for the damage itself because we wanted to know before. So if we see that those thresholds of temperature damage occurs, we could advise the farmer, well, now the risk is increasing and you need to do something. What can they do? Obviously, they could use micro sprinklers to cool the system down, or they can use coating, reflective coating, to avoid the incoming energy from the sun. All that could be done, or hail nets is also obviously something to protect permanently. So then we went...
So we are here in precision horticulture, which is basically a story about sensors.
To build up a system for measuring.
A laser scanner. It is scanning those trees, apple trees here, and we get 3D point clouds from the scanner. And what we do then is we use those plant information into models that will help the farmer for also in the future providing the fresh fruit that we need.
Yeah, so we have this circular conveyor over 90 meters along a tree row, or here a row of apple trees. And we use a laser scanner to circle around the trees to monitor them, well, theoretically 24/7, but well, that is not what we were able to do, but for a long time at least. So we, unfortunately, I cannot start the other video. No, I cannot. All right, well, so you would see on the right side how the sensors are moved along the trees. So there is this laser scanner, and then there's also a thermal camera. We fuse those data, and by having the geometric information from the laser scanner, we glue the thermal information from the thermal camera
we get the 3D information of the temperature distribution. And this is how it looks like then. So you get a nice 3D point cloud that you can turn. So you can look inside. It's not like just having the front view, but really you can turn the whole model around. And what we see here in false color is the temperature distribution. So we can see already that within the canopy there is temperature distribution variation. But we are not so much interested in the canopy temperature, although that is interesting as well, maybe for irrigation treatment. But we were interested in the fruit. So we segmented out the fruit. So the colored points that you see now, they are individual fruit. And you also see the different temperatures then. And what we can do with those information, well, first is we have the position of the fruit. We can calculate the size of the fruit. And we do have the temperature of the fruit. And we can do all kind of calculation, like you may know the crop water stress index, where we consider the highest and the minimum temperature into the crop to say if it is stressed or not stressed. And here we can do the same with the fruit. So we pick out the coldest fruit and we pick out the hottest fruit, and then we calculate this fruit water stress index. So that could be done in 3D. However, only with this temperature information, I think that is quite interesting already. So, because if you have a look on the diagonal curves, so these yellow triangles, they indicate the diagonal curves of the air temperature. And then the green-blue box plots that we see is the temperature of the fruit. Let's have a closer look, or maybe on that side. So we see there is a distribution, right? So for each of those plots, there is a distribution. That means we have the air temperature having a certain diagonal curve. Of course, during the day, it's warmer than during the night. However, the fruit is following this trend, but not exactly. So there is a time gap between that, and that is kind of logic because the fruit have a mass. They need to warm up, so if the air temperature is increasing, it needs some time that the fruit is also increasing temperature. And then it's not just one point, so it's not we have the air temperature and we have one point with the fruit temperature. It's a whole distribution. That means it's not the case that all fruit are facing the same stress, or each fruit is facing its own stress, like humans. Yeah, but here we can measure now. So by having these 3D point clouds annotated with the temperature, we can measure those distribution. And that might be helpful to do some more specific application, like if we think about coating, we could coat especially those areas in the canopy which are hottest. So we could think about a little bit more. This is still research, so I want to say we can get more precise and we gain new information that were not available before. Because before, as said, so we had the thermocouple, so we could measure it maybe in one canopy. Here with this system, we measure something like 112 trees with one circle in the conveyor row. So we have thousands of trees and hundreds of trees and thousands of fruit. So with all those data, we can build more robust models then. So and you see this pattern with these daily curves easily. So if we model that with a thermodynamic model, it's basically the same curves that we get. So we can have the impact factors like the sun radiation, the angle of the sun radiation that changes over the year. We can have the mass included. We can even have the color of the fruit included, because according to the color, it absorbs more or less fruit, and in which wavelengths the absorption takes place. That can all go into this kind of energy balance to model how the fruit is heating up during the day and then cooling down during the night again. And if we do that with a kind of a thermodynamic model, it basically looks like a Zeno's function thing. That is a good start. And then because we had this pattern, we
use that in a neural network to predict the risk. So we went into the orchards and had a look, when did the damage occur? So what kind of damage was it? And then we just said, well, it is a damage or not, because it was too tricky to say, well, this is bleaching, browning, or necrosis. We could just say, well, we have a damage or not. But this is what we implemented then in a neural network. So what you may imagine, we need the weather information, because without the weather, we cannot really make a prediction here. So, and we use the satellite data. Obviously, that is also a little bit erratic, or with, let's say, with a high measuring uncertainty. So I move over here again. So we see here the global radiation bioweather station on the x-axis, which was directly placed into the orchard, and then on the y-axis, you see the satellite data. So there is deviation. So we cannot be super precise here, but what to say? I mean, the satellite data come for free. So that means if we have this mobile app, and you may download if you want, so if you have the mobile app, you don't depend on any sensor for the moment. So, but you have a measuring uncertainty. So that's why we said, so maybe if we have this app that tells you maybe that there might be a risk in your orchard. So we have made it for different cultivars, apple and grape species. So there might a risk appear, but then you can give feedback. So the user can give the feedback to the mobile app and download it anonymously and say, well, but in my orchard I didn't see anything, so there was no damage. So and then you feed that back. And by that, we collect more and more data, and at some point, we will have, hopefully, something which is more reliable and adjustable to the different orchards. So that's the idea behind it. It's basically pure digitization with all the benefits. So you can have the information not being in the orchard. You can have it at each time of the day, whenever you have time to look into it. And it may help to make decisions then on the crop management. So far, so good. Thank you so much for the attention, and thank you.
Thank you, Manuela, for this interesting presentation. I think there will be many questions. One moment.
Thank you, Manuela, for the very interesting presentation. I assume that extracting fruits on top of the canopy is a challenge. Are there any relationships between fruit temperature and the temperature of the canopy that surrounds it?
Yeah, of course. Let's go back to the point cloud maybe, because then it's easier to see, or maybe that with a fruit. So we have different challenges here, and I didn't touch any of it. So one is if we are measuring, so what you see, what is colored here is, no, the other way around. Everything that is gray and colored is a fruit, but only some are gray and only some are colored, and only those which are colored are temperature annotated. So that means the thermal camera, the LiDAR sees all the fruit, but the thermal camera can only see some of the fruit. So that means we can only color, annotate some of those fruit. And you see the one in the top, we didn't color at all. So there are two reasons for that. It might be that the thermal camera didn't see it, but it might also be that it is too erratic. Because we have issues when we fuse the two sensor data, especially the branches on top, they might be windy conditions and then they move. So one sensor is measuring here, and then the thermal camera is coming through, which is only a few centimeter distance, but still, and then the wind moved the branch, and you're out of view. So which means that the annotation might have some problems here. So another issue is that the thermal camera may see through the canopy and may annotate something from the sky even. So that is all causes of error, sources of error. Well, but that is in each method, right? So that's why we try to stay safe, and we only annotate the middle part for the moment and keep out what is too difficult to measure. Does it answer the question? One more?
I guess what I'm trying to ask is whether you can use, instead of the fruit temperature, the canopy temperature which surrounds, might be easier to collect.
Theoretically, yes, it's much easier to collect, but well, we have the air temperature that is easy to get. So we have the satellite data. That is one thing. Then we get next level, which is a local weather station into the orchard. And then you get microclimate sensors. So there are many IoT sensors around for measuring the microclimate into the canopy, having the temperature and the relative humidity mostly. Sometimes also global radiation or wind speed. But then it's only the canopy, it's not the fruit, because the fruit is also having properties, like we have different heat transfer coefficients, we have different mass, and we have different color of the fruit, providing different absorption properties to the incoming radiation. So each fruit is really different. So I doubt that we can reliably predict the temperature of the fruit from the surrounding. I think measuring is always more safe. Although at some point it might be interesting to do that, sure.
One more question? If not, then again, thank you very much for this interesting topic. And thank you very much to the auditorium to be here. And I hope you had a nice time here. We had a lot of very interesting presentations. And then thank you very much for the speakers, and I wish you a nice day.